First, I want to briefly talk about why things change. When I mean change, any change. There could be structural change or any chemical reaction change. Any change, there should be a reason. And I hope you remember this Gibbs free energy equation. Any change is favorable if you lower the Gibbs free energy. And that comes with the two terms. When you lower the enthalpy or increase the entropy. In short, instead of the free energy, I want you to look at the potential energy as guideline. If any change takes place, you can consider that it is because of the potential energy has been decreased. Potential energy is the energy stored in the molecules. And there are four types of forces in the universe. Strong force and weak force. Those are working inside of nuclei, so you don't have to worry about it because it doesn't affect chemical reaction in most of the time. Then one of the weakest force for the light molecule is the gravitational force. Again, because gravitational force is weak for the small molecule, you don't have to worry about it most of the time. So the only force among the four fundamental forces that we have to worry to evaluate the energy stored in the molecule is the electrostatic, electromagnetic force. The potential energy, like a Gibbs free energy, is a static state energy. They can be expressed on the chart to represent the energy inside of the molecule who are different from state. Most of the time it means they are in the different environment or they are different molecules. So on this chart, this molecule has higher potential energy. This one has lower potential energy. If they are related, such as this was the initial state and that was the final state, then the compound, that is the reactant and the product, therefore the reactant somehow lost the potential energy from inside of the molecule to the environment, end up having lower potential energy. Just like the Gibbs free energy, the system is naturally changing from the high potential energy state to the low potential energy state spontaneously by releasing the energy in many various forms such as heat, light, etc. However, if you want to go against the natural process, then you have to give them energy. So the given energy will be stored in the product and turning into the reactant, the original reactant that happen to have more energy. So this means that given energy from outside of the system will be stored in the system, such as the molecule, and they create unstable state in a given energy condition. Okay, the given energy can be, most of the time in chemical reaction, heat energy. The heat energy is average kinetic energy of molecules. So when you raise the heat, you are providing the kinetic energy for them to overcome the energy gap they are facing to turn into the new state. That is the kinetic energy. But what is potential energy then? Using electromagnetic force, the chemical in our case can make up a certain potential energy. For example, when you have a positively charged particle and negatively charged particle, A and the B, for example, we can say they have different potential energy because potential energy depends on the distance between two objects. In this case, the central particle, positive, has two different particles with the same amount of negative charge in different distance. So you can say the energy stored here, the potential energy is different from this potential energy. And also we know between the opposite charge there is attractive force, the electromagnetic force. And when you have a more distance, you have a less attraction. And there you have a more attraction. So we know this state is the state that can release more energy as they approach, and that's able to become more stable. So if you apply the situation to a given diagram, the final stage is corresponding to B, the more stable with the more attraction. And A can be seen as the initial I, energy, initial state. So if you let go of the A, it will end up having state like a B, and it might end up going closer to the positive charge. Alright, with that being said, if you want to force the state B, which is the close distance between the opposite charge, with more attraction in more stable state, and you want to promote the distance to be increased by pulling the B away from the positive charge, then you have to give the energy against the interaction here, and that is the something we talked about earlier. You have to give the kinetic energy to move the particle in the B state, which is the state here, and put it away from the positive, making you gain more. Gain for B, gaining more distance, you achieve the initial high energy state such as the A. And how much energy you need, it depends on the amount of the energy that's stored in here and here. That much of the distance has to be exerted to the B to have the B situation change to the A situation. Alright, now let's consider a different situation. This system has two positively charged particles with different amount of the charges. And without anything, these two feel each other and they have same charge, so they will push away each other. The given situation has a certain amount of the potential energy stored between them. However, if you leave them alone, they will move away from each other and it will end up lowering their repulsive force between them, meaning they are making themselves more stable and more stable if you gain the distance between them. So that process will be happening automatically, spontaneously, until they find the most stable possible states that can be achieved in a given situation. Now let's assume that you have an opposite charged particle introduced to this system. You would think that the negative charge will be attracted to the positive. That with the more opposite charge, plus 10 over 5, which is true. So around the 10, the negative charge feels more attracted and less potential energy will be stored and the energy will be lowered. And around 5, the negative charge will be feeling more potential energy, although it is attracted. We can assume that the potential energy is higher than the other state. So if you leave the negative charge here and it has a kinetic energy to move around, then it will eventually find better place here and it will naturally move to that. However, if you examine the given situation closely, there is a better place than here. Obviously, it's the middle section. Here's the negative charge place. It will be attracted by 10 and the 5 positive charge. So in between, the potential energy is much lower. So even the electron nearby positive 10 will end up be pulled and located more in between. So you can imagine the role of the potential energy to keep track of the movement of the negatively charged particle. And we know in chemistry, negatively charged particle is an electron. And the heavier nuclei with a positive charge are not moving as fast or as easily as the electron does. Therefore, the potential energy that we are using to keep track of the change is applied to the electron. And if you keep track of the electron movement using the concept of this potential energy, it's easier for you to understand chemistry. Alright, let's move to the next concept. In reality, the electrons are moving constantly. Even when they are located in the middle, they are moving around the shell for the smaller nuclei and also around the bigger nuclei. And they just spend more time in the lower potential energy state. So if you use this diagram, you can understand that as if the electron has enough kinetic energy, they can come up against this barrier and staying around here, around the bigger nuclei. So also you can go to the plus 5 nuclei. But obviously, although it's possible to come up here or there, but electron prefers to be in the most stable area, which is there. That's why the probability of finding electron is highest there, and that is called a bond. This bonding process, you can see that the electron feels more stable in the middle, and that electron is attracting this positive charge and that positive charge. So these two repelling positive charges are staying together due to the electron in the middle. And the electron in the middle is actually most attracted, so it has a power to hold these repulsive nuclei. And you have a bonding going on, although the electrons are constantly moving around. So in conclusion, bonding formation is natural. Not in all cases, which I will explain later, but if the situation allows, that should be happening naturally. Also, because electron is constantly moving, the bond is not rigid. When you make a bond with a different atom, we show the bond with a line for a single bond. We really mean a roughly pair of electrons staying there, but in reality they are moving around. And if you think about it, when electrons move around, they repel. Depends on the situation where how much electron density is here. If that fluctuates, then these repulsions are fluctuating, and that can be a contribution to the repulsion and attraction when electron comes in, so it can cause changes in vibration if you are distributing the electron density here. Also, you can expand this model, which you always have to imagine as you do chemistry. You can understand concepts like electronegativity. The effective nucleus charge that's holding the valence electron regardless of the inside electron number. You can calculate the effective nuclear charge that leaks out of the inner shell, reaching out the valence electron. Then you can imagine how attractive the nuclei is for electron. So say this electron feels plus 10, then this atom is more electronegative, because the definition of electronegativity is the degree and potential of the nuclei pulling electron toward itself. And less positive nuclei attracts electron with less power, so it is less electronegative atom. So in this given situation, the B, which is the one that has the plus 10, is more electronegative atom, so the electron is not going to stay in the middle of the two atoms. The electron's moving toward the B. So that arrow showing the movement of the electron, and that is called dipole moment. As the electron shifts, that means the electron spends more time around B because it feels more attracted and stable. Then the nucleus charge of the A is not completely cancelled, because electrons stay less now due to the B, causing more stability, and electrons spend more time with the B. Nucleus charge leaks out, and the outside of this chemical we can measure some partial positive charge. Then over here you have more electron density than the neutral state of the B. You have more negative charge than the nuclei. So you can say B is partially negative, and that is the polarity how polar the molecule can be. I want you to remember at least the order of the electronegativity for these common atoms. If you can, please do memorize the numbers. So, in the neutral state, fluorine has the greatest electronegativity than oxygen. Then nitrogen and chlorine has the same electronegativity. Then you can see these bromines and carbon, sulfur, iodine, they have both about same electronegativity. This corner of the periodic table shows greater electronegativity atoms. Then as you go away from it, you have a relatively small electronegativity, especially these metals, these non-heavy metals. It could be even as low as 0.8, 0.9. The electronegativity difference between this side of the atom and this side of the atom can be too great, so they may not be able to share electron in covalent bond. For electron, it probably would be better if they jump onto the shell of these electronegative atoms, non-metals, to form ionic bond. Okay, then let's talk about a little more deeper understanding of changing electronegativity and size. We should not think the electronegativity of a certain atom is fixed and constant, as well as the size of the atom. Say fluorine, we said the electronegativity of fluorine was 4.0. But it is not always the case, because by the definition, electronegativity is the ability of holding electron. So for fluorine, it's not always same, because fluorine can be part of the bigger molecule, and the bigger molecule compared to another molecule where you can find the fluorine can have a different structure and different amount of electron. Then fluorine might have different potential energy level for electron. So I want to talk about those things in more detail. You're looking at a diagram. It's intended to show you the carbon. You're not looking at the quantum picture of the atom. It's just a classical understanding of atom, and we are using it just for now. The nuclei with a 6 proton, then you know you have 2 electrons located and moving around on the first shell, and that's only consists of one s orbital. Then the remaining 4 electrons are on the second shell, 2 in the 2s, another 2 unpaired ones in 2 different p orbitals. And these 6 protons are pulling these 2 electrons in the first shell. But because they are negatively charged, in terms of charge, the amount of charge passed through the first shell is, after cancelling 2, lost by the 2 negative, you only have a plus 4. So these 4 electrons on the second shell, they are pulled by the nuclei by plus 4 effective nuclear charge. So when you increase proton number by 1, then you are looking at the nuclei of nitrogen. Then this first shell is not anymore feeling plus 6, but they are feeling plus 7. And then the charge leaking out is not anymore plus 4, but it's plus 5. So whether you have 4 electrons or 1 more electron for nitrogen to be 5, it doesn't matter, they are pulled by plus 5. But compared to the carbon, the second shell of the nitrogen is attracted by bigger plus charge. So those shells, those electrons in the shell, is making up the shell. There is no rigid structure of the shell. The shell is the place where you find electron. Thus, you can say electron determines the shell, its size, and its electronegativity. You can say, since these electrons are now more attracted compared to the dose of carbon, they are getting closer to the center. Therefore, the size of the valence shell shrinks. You can continuously continue the concept. One says, if you can add 2 more protons now, you are looking at flowing. Then you have a 9 proton cancelled as you pass through the first shell. You have plus 7. So the valence shell has more electron, but each one of them pulled by plus 7, therefore the size decreases by a little. However, they don't shrink so much. That's because the electron present on the shell now is not 4, but 7. So you have to think about the repulsion that resists the shrinkage, so it doesn't shrink as much, but it does get smaller. Therefore, as you walk the second row of the periodic table from the left to the right, you can imagine more powerful attraction from the nuclei, and the size of the shell decreases, and it becomes more electronegative. Then they are more neutral. But if you go to the third shell, you have enough of an electron on the second shell, you're not able to squeeze more electron in because it reached the maximum repulsion between electron. So, example, when you have a chlorine, you have a 17 plus charge. Then the first shell cancel out 2 charges. So you have a 15 plus holding the second shell. You have 8 electrons on the second shell, so that's leaking out is 15. What's leaking out is 15 minus 8, so it is again 7. So just like the fluorine has plus 7 holding the electrons on the third shell, so they feel the same amount of charge. However, compared to the fluorine, the electron on the valence shell, which is third shell, is located much farther from the source of the plus 7, so the attraction is less. Therefore, the potential energy is much greater, less stable electron. So its shell shows less electronegativity. Alright, I want you to remember our first question of the class was why things change. I meant why things change naturally. In the earlier video, I told you that we can go back by giving force against the natural process. But in simple, why things change naturally, such as a reaction or geometry change or solvation and melting, whichever the case might be, that is due to the potential energy has been lowered by doing so. And our focus was later more on the electron and nuclei. In that situation, I want you to remember it was due to the stronger attraction in the product. compared to the beginning, afterwards through the change. If you are able to get more stronger attraction, then you can lower potential energy by losing distance. Meaning by getting closer when you have opposite charge. Or we didn't talk about it yet, but you can think about the situation where you can more greater charge. You can have a more greater charge, stabilize it. Then you can also lower the potential energy, and that's what the favored situation is. What if you have the same charge, then when you have a repulsive electromagnetic force, then you can lower the potential energy by gaining distance, meaning by going away from each other. So just like our happiness, for chemicals, the potential energy is measured this way. When you are attracted more, you feel happier, you feel more stable, and you have a lower potential energy. When you are repelled, you feel like you are hated as a human. That's when you feel higher and more potential energy. That's when you are not stable, and that's the state you promote your reaction and changes by losing the potential energy. So we can guess and predict why some change is happening if you are able to figure out the attraction and repulsion. But we further talked about the situation where you have to judge electronegativity and size in bonding. Simply speaking, you can have a carbon that's bound to the 4 hydrogens, and the carbon has a more effective nucleus charge, and it attracts electron toward itself with a more electronegativity, and carbon uses second shell. But when you compare the same carbon after having one replacement of hydrogen with a fluorine, then still the hydrogen electrons are taken to the carbon. However, the second shell electron of the carbon taken to the fluorine, because fluorine has more nucleus charge, so fluorine ends up becoming partially negative, and the carbon becomes partially positive, and hydrogen becomes more positive than before when it's only bound to the carbon. And here in this compound, the carbon is partially actually negative, while the other carbon is positive. So if you think about electronegativity of these two carbons by remembering the carbon electronegativity is not fixed, but it's just the property of attracting electron to itself. So when carbon is partially negative, it is possessing more electron than 6. And here, this carbon lost electron to the fluorine, so it has less electron than 6. So who has more ability of attracting electron? Obviously the carbon that has partial positive. It still has partial positive leaking out, and it has more room for the second shell by losing it, and it has less repulsive situation. So when you attempted to give electron to the both of the carbon with the fluorine on it will have a more chance to gain electron. So the electronegativity changed. Therefore, we can also say size has been decreased from this carbon by losing electron, by the repulsion among the electron on the second shell decreases with the same attractive force from the center. The electron able to come closer as the shell shrinks. As the shell shrinks, the electron feels more attractive force because they are getting closer to the nuclei. Thus, they are able to lower potential energy as we talked about before. So, this is our first video, and I hope this is helpful for you, and I'll come back with a more video. Bye!